probably heard of this thing called the butterfly effect. It's a term we get from a branch of science called chaos theory. The idea that weather prediction is impossible because if a butterfly flaps its wings, that input is going to change the output and you're going to get hurricanes instead of sunshine in Tokyo 2 weeks later or something. And over the last few decades, mathematicians everywhere have started studying systems in a different way. For a long time, maths was only interested in problems you could solve. Give us the solution. If you can't give us the solution, this problem is not interesting. We're just going to go and find something else to look at. But mathematicians kind of embraced this whole different school, a different way of thinking. We created imaginary numbers. Now, the basic rule of an imaginary number, we have this number I, and in the natural world, negative numbers don't have a square root. 2 times 2 is 4, minus 2 times minus 2 is also 4. So how do you get what times what equals minus 4? Well, nothing, it doesn't exist. And mathematicians go, no problem, we'll just make something up. We'll invent I, it's an imaginary number, and I squared equals minus 1. And this is where the rest of the world goes, you can't do that, and mathematicians go, we can do anything we want. It's imaginary, we don't care. But then once they've developed this and they've come up with a rigorous set of mathematics around it, you can do some really interesting things with it. Now, this thing here, 0.8 plus 1.2i. Hang on a second, give me 1 second. There's a bunch of slides that have gone missed here, and this is not making a huge amount of sense. Yep, no, we're good. One slide is missing. Right. Now this number here, 0.8 plus 1.2i, this is what's called a complex number. A complex number is like a project plan. It has a part that is real, and it has a part that is imaginary, and it is very difficult to predict what is going to happen next once these things get involved. Now, there is a whole study of systems and the behavior of systems that we can talk about. This thing here is called an Argand diagram, and the blue bit is imaginary, the red bit is real. So 0.8 over there and 1.2i plotted up there, and this way we can plot numbers in complex mathematics in this kind of space. And we can do arithmetic with these numbers, just like you used to do in high school. So we take 0.8 plus 1.2i, you just expand the numbers out as you go, and you multiply, and all you need to do is remember that anywhere you have 2 blue numbers multiplied together, the result is going to come out negative. It's going to come out backwards. So this 1.2 times 1.2i, well, you square them, but then you stick a minus on the beginning, and you take negative complex inputs, you get complex numbers out the other end. Now, what's really interesting is when you start studying the behavior of systems that are driven by these. Let's take a really simple function here. We're going to take some real number x, so we're back in ordinary mathematics, and every generation x is going to go to x plus 1. So 1, 2, 3, 4, and you can already intuitively see, you know how this system's going to behave. You can be confident you understand its behavior all the way up to infinity. Let's try another one. So if we take this example, x equals 2 minus x. It's going to go to there, 0 minus 2, 2 minus 2, 0 minus 2, round and round and round. If we apply the same thing to this complex number, what we're going to do is we're going to keep taking that number and squaring it. First time we square it, it goes to here. We square it again, it goes to here. We square it again, it ends up over here, and then over here, and then it disappears, off to infinity. We're going to move it ever so slightly, and we're going to run the same sequence again, this time 0.6, and it goes to here, and here, and here, and here, but it doesn't escape this time. It goes into this little kind of weird, almost circular orbiting pattern. Now, those 2 points are right next to each other, but they exhibit dramatically different behavior when we iterate them over and over again by squaring them and squaring them and squaring them. And eventually, this one disappears. Now, the first really rigorous study of these kinds of systems was done by this guy. It's a Polish mathematician called Benoit Mandelbrot. And Mandelbrot was fascinated by the mathematics of real life. He had this quote, "Clouds are not spheres, mountains are not cones, coastlines are not circles, a bark is not smooth, nor does lightning travel in a straight line." Now, Mandelbrot had a brilliant job. He taught mathematics at Harvard. And when he got bored, he went to IBM and played on the computers. Because this is the 1970s when IBM had computers and nobody else did. So he would come up with these, wonderfully complex mathematical ideas, and then he'd go over to IBM and spend a couple of months playing around and simulating them, and then he'd go back to Harvard and, talk to his graduate students about all this kind of stuff. And he was the first person to see the shape which now bears his name. His name was Mandelbrot, but everyone calls it the Mandelbrot set, and I know that I'm going to do that, so let's just call it the Mandelbrot set. Basically, he took each of these numbers in this grid, and he said, we are going to square this and add it to itself, and square it and add it to itself, and we are going to see whether it stays on the grid or not. And if it stays on the grid, we are going to color it in black. And if it disappears and vanishes off the grid, we are going to color it in a different color depending how quickly it, what's called, tends towards infinity. He started off with these very, very low resolution renditions of this image, but the one that you're probably used to, the one that all of us have seen, is this, the Mandelbrot set. Now, the astonishing thing about this, from this incredibly simple mathematical rule, there is an infinite amount of complexity. We're going to take a Mandelbrot set here, and we are just going to start magnifying, and we are going to start zooming in. And when we get to around about here, we're going to say that's 1 times magnification. And we're going to keep zooming and zooming and zooming. And by the time we get to about here, that original shape is now the size of this building, and we are still zooming in. When we get to around about here, that is 2 to the 20 factor magnification. The original shape is now bigger than London. And we are still zooming in. And around about now, the original shape is bigger than the United Kingdom, and we are still zooming in. And we are still zooming in. And we can continue zooming into this shape forever. It never repeats. It is what's called self-similar, which means it resembles itself at different scales, but it never repeats exactly. There is an infinite amount of detail buried inside this one shape. And this has been there the whole time. Nobody invented this. We discovered it. Now, the Mandelbrot set, some people have called it the thumbprint of God. Now, I'm not a very spiritual person, but I do play a lot of computer games. And I love that thing in a computer game where you're doing something silly that maybe isn't part of the main campaign, and you find that the game designers left something there to persuade you that you were supposed to be here and you're on the right track. And this thing has been hidden in mathematics since, our universe was created. And no one ever saw it until we humans, we invented computers, which means taking lightning and sticking it in a rock until it learns to think. And we invented advanced mathematics. We invented high-definition color displays and rendering technologies, all this kind of stuff. And this is what we found. Something that was hidden there the whole time, nobody had ever seen until we built the machines and the technology to allow us to visualize it.